and thanks for the invitation for the nice conference. As it was a long time ago submitting this, so I just added also to the title that it's elastic excitation. So I will talk this toward the end. So here we have this work basically local collaboration in Gothenburg University. The main players, the experimentalist Shreyas and Admir, those are PhD students, and we have some feedback, theoretical feedback from Roman Kremen, and of course the collaboration with Professor Ackerman and Dag Hanstrup, the head of Photon Factory here in Gothenburg University. And I think Schumack was a nice introduction for spin wave and its importance. So basically what we need to know that spin waves are waves and are bosons, quasi-particles that have a smaller wavelength than its electromagnetic counterparts, and that can be used for technology to replace like electric charges. So typically, as Schumack mentioned, so it's to excite the spin waves, it needs to be used either inductive means or like current, either spin current or some polarized charge current, where you can excite those spin waves, and of course those has limitation either from detection or the excitation using our current electronic system. So in order to make better electronics, so we need to excite spin waves at much higher frequencies and smaller wavelength, and this we can use the advantage of the possibility of using like optical excitation, which does not have the limitation of the electronic excitation or detection. And of course, this would go for the application in magnonics, like mentioned by Schumack, multiple very nice devices, as he mentioned, those mainly from his group and his nice review in Nature Physics. So, and also like he mentioned also neuromorphic computing, like using spintronic magnonics, but also there is also the importance of magnet for those new devices based on hybrid magnonics, where you can hybridize magnons with other quasi-particles so then you can use the magnonic tunability and nonlinearity to tune the response to where you need. And this is, I think, the new direction that magnonics are going to flourish in. And so if we go to the optical excitation, so it's ultra-fast demagnetization is the prime method to excite with femtosecond pulses, femtosecond laser pulses, and as this like pioneer experiment on nickel. So here, if we have ferromagnetic metals, what happens is that the optical energy goes to the electrons, then it dissipates this heat or the energy through the interaction between lattice and spin, and this will give very rapid demagnetization in few picoseconds. And also it was recently shown that one can manipulate the magnetic order in attosecond even. And also there is another effect, the inverse Faraday effect, where basically you have the magnetic field from circularly polarized light. You have the helicity right or left that can impose a field to mostly insulator here, then you can control the magnetization, and you can excite spin waves with this method. The important thing that we would focus on the generation of the spin waves, and that, as I said, that this is very fast and also most energy efficient way to to excite magnetization, as this, for example, here it shows that it's in picosecond, and it requires just like few atto joule of energy. And the problem here realized that you have this dumping of the magnetization. So most of the experiment normally use stroboscopic measurements to study this oscillation that happens in to just few nanoseconds. So you can amplify this response and make it live longer using like coherent amplification, where you basically come with a second pulse that keep the excitation going. So if it's in phase with your first pulse, it will amplify the response. You can quench the response if you have anti-phase, or you come at middle of the period. And here this is shown. This is for antiferromagnet, for example. And this gives you additional control also by using, for example, the chirality or the handedness of the light, where you can keep basically amplifying in a certain direction. So we take this idea, so we use the optical excitation for demagnetization. Then basically if we come before the dissipation of the spin waves, so we can basically keep them in a steady state, like auto oscillation. So we come with one pulse, and then if we pulse it before it dumps out, we can revive the oscillation, and we need to be in phase with the spin waves to keep it on and amplify it. And and this had been done by the pioneer experiment on Yig by doing exactly this thing, and it can excite here using inverse Faraday effect, like steady state oscillation in Yig. And this also had been used in hybrid magnonics with photon magnon, where you can use now averaging technique or non-stroboscopic technique, and we use this idea we implemented in the brilliant light scattering averaging technique, and we use the microscopy so to study the spin waves. And our setup basically is here, and it's based on brilliant light scattering, where you basically lose energy or gain energy by scattering to a magnon that would change the wave vector of the light, and would give you like satellites and stocks or anti-stocks, and the emission will basically based on the K vector. So we have limited resolution to the collection angle of the objective. And of course, we can select to measure the spin wave using the analyzer, or we can study any other quasi-particle, for example, like phonon, longitudinal phonons, by just measuring at the same polarization of the initial light. And we can move the probe around, and we can move the sample as well, so we can make mapping of the excitation. And our initial experiment was published like last year in PRP, where basically we studied in permalloy 20 nanometer thin film. So this is the spin wave response in iron nickel permalloy, where we have the ferromagnetic resonance and the spin waves here, the limit cutoff of the K vector due to the objective. And if we apply the femtosecond now with 5 milliwatts, we can see like we start to have some additional spikes at harmonics of 1 gigahertz, like here we see. And those are mainly around the magnetic response. And this here we have like logarithmic scale that we can see that this increase dramatically. And we know from PLS we are measuring like the square response of the magnetization fluctuations. So we can present this like, for example, 8 gigahertz, which is around the FMR. And we see basically that on the overlap between the excitation, so it's at the point source, we have dramatic excitation of the spin waves that can fit to a Bloch law model that we make very simple. Bloch law model that basically tells us that the spin waves comes basically from the demagnetization or the change of the heat path of the magnet. And this is 1 micron away, so this is kind of propagating away. And if we see the field response here without the femtosecond excitation, and here we can see like with low power and this increase with power at with 1 gigahertz separation due to that. The repetition rate of the frequency comb that we are using is 1 gigahertz. So it's basically everything in phase with this repetition rate we are getting amplified. So here we have the selectivity of this spin wave. If we study the profile of this, we see that it's basically extending to the areas around here the center of the probe, and this is around it. And we can estimate the propagation length to be around 1.8 micrometer, like would say typical for permalloy. And if we make a map of the spin waves, we can see on those harmonics that around the ferromagnetic resonance. We can see localized mode just below the FMR, then FMR, and then some propagating spin waves. And the field is applied in this direction, so the spin waves is traveling perpendicular to it, and we can verify that by tuning the field direction, and we see that it's still perpendicular to it. We can simulate this using MOMAX and simulate the recovery of the magnetization after the demagnetization, and this would work. And we see like very nice resemblance between the experiment and the simulation. So those modes that we are detecting at high frequencies, those are propagating spin waves. And if we look on details of the field, we can see that there is the highest excitation is around the FMR, but then there is something below it, that it's those localized mode and then the propagating modes. So we make scan and we make profiles of those modes, and we can see this is those points are the FMR basically. And then we have below that localized mode, because those are in the spin wave band gap, and above that we can have this chaotic shape of spin waves, and those are changing the angle basically if you change the field, and still here the field in one direction. So this gives you a nice opportunity to control basically the propagation direction, like here in optics. And the physical reason behind that basically you have the anisotropic dispersion of those spin waves here. We can calculate this theoretically, and we see that it's reasonably agree with the experiment. This was published. It's here in PRL. And now if we see that this works for one thickness, for one material, let's change the thickness and see what happens. So we measure at higher thickness now, like 20 nanometer is around the penetration depth of the laser. The femtosecond laser is like near infrared 820, and we see for 40 nanometer the response sustain, and this is as a function of the fluence of the power of the laser. And we can see that we can have the similar features that we saw previously, and it fits this our model based on the Bloch equation that fits very well to those spin waves, like 8, 9. So those spin waves around the FMR and above it. And we still have the same reason of this. And if we get going higher, so we just having this on the surface, can have for 60, for example, we see that we start to excite the perpendicular standing spin waves that are in the system. But first, if we compare those, for example, the FMR excitation in all films, we see that basically when we go To thicker films, we get very much less response due to the redeposition of the energy, and we can basically fit this A parameter, so the amplitude of this to to 1 over D corrected with the absorption at low thicknesses. And so then we saw this the perpendicular standing spin wave excitation, and this is nice thing to verify the excitation efficiency of the technique, as it's those pieces W have 0 wave vector, so they do not depend on the collection angle of the objective on their detection. So we go for 100 nanometer, for example. We see those different pieces W's. We can fit them to the theoretical equation, and those fits well, and those gives nice comparable parameters for all our films. And we see that basically when we put the laser on, the femtosecond laser on, we have high excitation of this first perpendicular standing spin wave. This is the FMR just here, and this is the first, the second, the third. So we can see that the excitation of those perpendicular standing spin wave, basically due to this, like the stratification now of the energy, so it can couple better to those standing spin waves. And we can see that this basically sustain up to 15 or 16 gigahertz. So using 1 gigahertz frequency comp or repetition rate, we can go to 16-fold multiple of this. So this is very nice. So as the frequency comps can get to like hundreds of gigahertz, one can excite basically any frequency selectively. Any frequency selectively, and this would be nice like for ferromagnet, antiferromagnets, and also for the spaces W's that can go to very high frequency at low thicknesses. Now everything we looked at are the spin waves that follow the Bloch law on the excitation power. If we now tune to another material, which is nickel, like we see that most of its response are on like the phonon part or the elastic part. So here we are analyzing the phonon channel and PLS, and we see its response follows like square dependence, so it's linear dependence on the power, which is expected. Now if we see the maps of the excitation of this, so here we have nickel 100 nanometer over quartz. So we see with on different two different substrate with like the Z cut and the X cut. So the Z cut is here. So we see like we have a pattern of like resemble the symmetry of the cut of the lattice, and this is reflected on those different harmonics. And basically we have this kind of the phonons phase is resolved directly, and this is something we're still trying to figure out why. So here we are detecting this surface, let's say phonons or longitudinal phonons that are basically affected by more bulkish like surface acoustic wave like PS AW. And if we calculate from those the wave vector, we can see basically that we get the sound velocity that it's reasonable for nickel on quartz. So we do this on sapphire, and we see for like two different cuts of the substrate, we are getting this nice shape for like the C cut, the hexagonal shape over those phonons, and with this like R cuts, we have this symmetric, and also we can calculate the sound velocity, and we can get the elastic parameters of those. So this is the new result that we are working on. So this is good direction to go for like hybrid excitations and like magnophonon or magneto elastic excitation and those materials. I think this still need to be discussed, how we are getting the real space phase resolvents on this directly on the PLS. But we can get more information on this if we take into account now we are exciting with one laser. So this is also another nice thing about exciting optically, that one can get like a shape of the laser focus, like multiple points, etc., or any shape. So here we use double points. So we have 2 focus points, and we are exciting this on the phonon channel. And we see basically that we get like the interference between those 2 point sources that resample the same wavelength of this phonon modes. So this is what we are working on, and we are evolving toward more like fancy hybrid excitations. But to conclude here, that we basically get a nice tool to excite spin wave and detect them, and we can model that and that with Bloch law, that basically based on the demagnetization of the ferromagnetic material, and we can get controllability over the wave vector, and we can have like acoustic behavior, and we can excite at least like 15, or even we got like 16 and 18 fold of the frequency of the repetition rate of the pump, and we can get to the PSSW, and probably we can get very high response with very low thicknesses, and we can get now resolved phonon, coherent phonon excitation on those materials. And with that, I want to thank you for your attention.
Yes, thank you very much for this fantastic talk, and it's a really cool technique. I think it's a unique one, and I have 2 actually technical questions. So what are the preconditions for the material? So if you can use YIG or any other material. And second question, what was related to the first one, what was the propagation length of spin waves in your case, and if it's possible to increase it?
Okay, thank you. Thanks for the question. Yeah, actually, this basically should be working in any material that excitable with the femtosecond laser. Now with YIG we can use the inverse Faraday effect. Unfortunately, we don't fabricate YIG in-house, so basically we can collaborate and have those samples and do some fancy stuff with that.
Yeah, we are very
yeah. The thing that the limitation of the materials, you need to have a good magneto-optical response for the readout for the PLS. So different materials that we had tried now, like nickel, permalloy, cobalt iron, boron. So all have responses. Of course, there are new things, and so each sample has something new. Like nickel, it's more elastic than magnetic, and so we still like characterizing those fundamental ones on like reference now samples. But I think that there is no limitation for materials. Also, we start like looking on ferrimagnets. I forgot the other question.
About how long the spin waves propagate in this experiment.
Yeah, now, for example, with those, we have permalloy. This was like a bad permalloy, let's say. Have high dumping, but still, its propagation length is like better than the literature, I would say. So this is still better, even it's not very good permalloy. Let's say. We have much better permalloy than this, but we did not try. So I think the coherency of those modes make them propagate much better. So for example, for YIG, those can go for, I think, we can reach millimeters.
Thank you very much.
For this great talk. Could you say again, for this nickel 100 nanometers micrographs you were showing, are those phonons or magnons or hybrids of those what we see there?
Those now are still phonons, so we are looking at just like the pure phonon channel, and we did not look at the like where we should look on for the magnetoelastics. So we're just trying to see firstly the elastic ones before going to the magnetoelastic. Of course, this is the 100 nanometers, so it's at the end of like the lower excitation. So if we want to go to more higher excitation, we need to go to thinner ones. I think when we get to 20 nanometer, there is we get this like kind of 50-degree shift, like signature of magnetoelastic excitation. But those here are phononic, just phonons.
Okay.